Hello everyone, welcome to the Luminous Science. In our previous video, we had seen about molecular spectroscopy and few of its application and the conditions to obtain the molecular spectrum in a spectroscopy. And today we are going to discuss about the vibrational spectra, which is also called as infrared spectroscopy. In our previous video only, we had seen that some spectroscopies need some of these specific conditions, like for example, to obtain a molecular spectroscopy, the molecule should have a permanent dipole. In the similar way, for a molecule to be active in the infrared spectroscopy, they should be vibrational. That means the bond should be having a vibrational energy level that leads to the occurrence of the infrared spectroscopy. Now, we'll discuss the topic one by one, which is involved in getting a pure vibrational spectroscopy and also some derivations like the energy level of simple harmonic motion. First, we'll see about vibrational spectroscopy or the infrared spectroscopy. So, for instance, we'll consider the consequence of elasticity, the fact that atom in a molecule do not remain in a fixed relative position but vibrate about some mean position, These spectra will originate from the transition which is induced between the vibrational energy of a molecule on the absorption of rotations belonging to the infrared region. These spectra will occur in a spectral range of 500 to 400 centimeter inverse. So, as we know that the infrared radiation will range from 500 to 400 centimeter inverse. So, when a molecule which is under the study of infrared spectroscopy, when a radiation are incident to those molecules, the molecule will absorb the radiation which leads to excitation of the electrons from their lower energy level to higher energy level. And here the specific type of energy level which we are considering is nothing but the vibrational energy level. And thus infrared spectroscopy is also called as vibrational spectra. So when the molecules absorb radiation which are in the range of 500 to 400 centimeter inverse, those molecules, the electrons which are present in the molecule will start vibrating, and due to this vibration there will be excitation of electrons from their lower energy level to higher energy level, which leads to the transition between the two different energy level, leading to the occurrence of the spectra. Now let us see what are the conditions to obtain the IR spectra. The important requirement for the molecule to give vibrational spectrum or IR spectrum is that the dipole moment of the molecule. So here also the dipole moment of a molecule plays a very important factor, and the dipole moment of a molecule must vary when the atoms are displaced due to vibrations. So, in molecular spectroscopy, we have seen that a diatomic molecule should contain a permanent dipole moment. But whereas in case of IR spectroscopy, when the molecules are under the observation and when there is a vibrational energy taking place within the molecule, the dipole moment of the molecule should change, which leads to the occurrence of spectra. So, like I said, the dipole moment of a molecule must vary when the atoms are displaced due to vibration. So, when there is occurrence of vibration, the molecule will be displaced, and due to this displacement, there should be change in the dipole moment. The condition required is only the change in dipole moment, and the molecule need not have a permanent dipole moment. Like as we have seen in molecular spectroscopy, a molecule should have permanent dipole moment, but in IR spectroscopy, the change in dipole moment should only occur when they are displaced due to vibration, and there is no condition that the molecule should contain a permanent dipole moment. Now we'll consider an example. For example, in case of a homonuclear diatomic molecule, homonuclear is nothing but same type of atom are involved in a molecule, such as H2, N2 and H2O2 etc., which have only stretching motion or vibrations and no bending motion or vibration. So in these type of molecule, that is in case of homonuclear diatomic molecule, since they are only same type of atom present in that molecule, so only stretching motions can be seen when vibrations occur and no bending can be seen since they're homonuclear, and also their mass will remains same. Since the mass do not change and the mass is same, or charge which the atoms contain are also same, so we can only see a symmetric motion, that is of stretching motion or vibration, and there will be no bending motion or vibration. The dipole moment does not change due to the charge during the vibration. Therefore, these molecules do not give a vibrational spectra, that is, they are said to be infrared inactive, since we can see only the stretching motion, which is a symmetrical motion, and since the atoms which are involved in homonuclear diatomic molecules are same, their charge will also be same. When stretching takes place, there will be no dipole activation, and thus they are said to be vibrational, and so they do not give us vibrational spectra, that is, they are said to be infrared inactive. And similarly, on the other hand, heteronuclear diatomic molecule, hetero means different nuclear diatomic, when a molecule contains different type of atoms like HCl, CO, NO, etc., and polyatomic molecules like carbon dioxide, water, methane, ethane, then etc., which shows change in dipole moment in some mode of vibration given the vibrational spectra are said to be the infrared active. Since these molecules are heteronuclear in nature, their mass will be different, their charge will also be different, due to which when there is a mode of vibration, apart from stretching, they also give us bending motion and also asymmetric stretching, which leads to the change in dipole moment, and thus we can see a vibrational spectra, and such molecules are said to be infrared active molecules. Now we'll discuss the derivation of the energy level of simple harmonic oscillation. First, let us see what is simple harmonic oscillation. If an atom displacement takes the path of parabolic curve, then it is called as simple harmonic motion. Parabolic curve is nothing but, we'll consider a thread and here is a ball. The movement of the ball in this direction and back again this direction, the semicircle movement of an object from its center is called as simple harmonic oscillation. For example, simple pendulum. We know that simple pendulum will move in a path of parabolic curve. This is called as parabolic curve, and for example, that is simple pendulum, and such oscillations are called as simple harmonic oscillations. Now, using the concept of quantum mechanics, it can be seen that if the vibratory motion of a nuclei of diatomic is taken as equivalent to that of the simple harmonic oscillation, then the vibrational energy is obtained using the Schrodinger wave equation. So we need to remember the Schrodinger wave equation, which is given by E vibration, which is equal to V plus 1 by 2 H omega oscillation, which is expressed in terms of Joule. Now here V is nothing but vibrational quantum number with allowed values of 0, 1, 2, 3, etc. This V, and H, as we know, is a Planck constant, and the omega oscillation is the vibrational frequency. We need to remember this equation, which is very important. This equation is nothing but the vibrational energy which is obtained using the Schrodinger wave equation. Now dividing equation number 1, that is E vibrational is equal to V plus 1 by 2 multiplied by H into omega oscillation by Hc to convert the unit Joule to centimeter inverse. Since the unit we are considering it is Joule, now we need to convert this into centimeter inverse so that our further calculation will be simpler and easier. And once we divide that equation number 1 by Hc, we get the corresponding equation, that is E vibration is equal to V plus 1 by 2 into H omega oscillation divided by Hc. So here H and H will get cancelled and will remain with E vibrational is equal to V plus 1 by 2 omega oscillation by C. And we know that omega dash oscillation is equal to omega oscillation by C. And thus we come up with another equation, that is, on simplifying this equation from the previous equation, E vibration is equal to V plus 1 by 2 omega dash oscillation, which is expressed in terms of centimeter inverse, which we consider as equation number 2. Now by putting the value V is equal to 1, 2, 3 in equation number 2, we get the following values for the vibrational energy. And as we know, V is the vibrational quantum number with the allowed values of 0, 1, 2, 3 and so on. E is the vibrational energy, and thus by substituting values of V in the equation number 2, we get the corresponding values. That is, for V is equal to 0, 1, 2, 3, we get the value of vibrational energy as 1 by 2 omega dash oscillation, 3 by 2 omega dash oscillation, 5 by 2 omega dash oscillation and 7 by 2 omega dash oscillation respectively. And thus it may be seen that the spacing between the adjacent vibrational energy level is always equal to Hc omega oscillation or omega dash oscillation, that is, the vibrational energy level of simple harmonic oscillations are equidistant. Like this is how it is explained. If we consider a energy level, that is, this is E. If we consider this as 0, 1, 2, 3, 4 and so on, it will continue 1, 2, 3, 4. So the distance between the consecutive energy level will be equal to Hc omega oscillation or omega dash oscillation. So the distance between each consecutive energy level is equal to Hc omega oscillation or omega dash oscillation. So from this we can know that the distance between the consecutive energy level are equal in nature, that is, an equidistant. And we notice that the lowest vibrational energy obtained by putting V is equal to 0 in equation number 2, and thus the energy level will be E naught is equal to 1 by 2 H omega oscillation, which is expressed in terms of joules. And also this can be expressed, if we want to express this in terms of centimeter inverse, and we'll simply divide it by H, which gives us E naught is equal to 1 by 2 omega dash oscillation centimeter inverse. The above equation shows that the diatomic molecule or any molecule can never be zero vibrational energy. That means if we put the vibrational quantum number value is equal to 0 also, then also the vibrational energy level of any kind of diatomic molecule or even a molecule cannot be 0. The atom can never be completely at rest relevant to each other. That is, the atoms in a molecule will be in a continuous motion. They cannot rest at a single point. The quantity 1 by 2 h omega oscillation joules or 1 by 2 omega dash oscillation in terms of centimeter inverse is known as the 0 point energy. So what does this 0 point energy actually means is, it means that even at absolute 0, when all the translational and rotational motion case in a crystal, the residual energy of vibrant E naught still remains. That is, the vibrational motion still exists. That means even if the vibrational quantum number value is 0, and in some of the cases of molecules, the rotational energy and translational energy may also be 0, but the vibration within a molecule due to the movement of electrons can never be 0. And still there will be the existence of vibrational energy, and thus though the value of a vibrational quantum number is 0, the vibrational energy cannot be 0. It will at least have the value of 1 by 2 h omega oscillation, which is expressed in terms of joules. And now let us see the selection rule which is involved to get the pure vibrational spectra. So for a harmonic oscillator, selection rule will be delta V is equal to 1 plus or minus 1, which is similar in most of the spectroscopy, like as we have seen in rotational spectroscopy. That is, the selection rule delta J is equal to plus or minus 1, and here also we'll see the same rule, that is delta V is equal to plus or minus 1. Now applying the selection rule, we might have from E V plus 1 to E V, that is, it is depromoting the electron from higher energy to lower energy. Then the value V plus 1 by 2 omega naught omega dash oscillation minus V plus 1 by 2 omega dash oscillation, which gives us the value of omega dash oscillation in terms of centimeter inverse. So this equation, that is depromotion of electrons from higher energy level to lower energy level, is simply called as emission. And in the similar case, if excitation of electrons also takes place, that is from lower energy level to higher energy level, the value will remain same, that is omega oscillation in terms expressed in terms of centimeter inverse. Now we'll see the determination of force constant. Vibration of a particle of mass m attached to one end of a spring depends on the nature of the spring. If the mass attached to the spring is pulled a little distance from the equilibrium position, it experiences a restoring force which is proportional to the displacement of the particle from its equilibrium position. The spring showing this type of behavior will obey the Hooke's law. And with the vibration of the spring, the particle attached to the spring also undergoes a periodic motion. The atom in a molecule which are joined by a bond are not at rest but are vibrating constantly. Like, we'll understand it by considering a diatomic molecule HCl. The atom H is attached to Cl by means of a bond. Let us consider this is a bond. The bond is in a form of a spiral. This atom vibrate constantly with respect to their mean position as seen in the figure. So the first paragraph which we have seen, that is in vibration of a particle. So here there are two atoms which are present, that is one is Cl and the other one is H with their respective masses, and they are separated by a distance of r, which is called as the bond length. Now due to the vibrational force, if these molecule, any of one of this atom go stretching, so the stretching energy of a H will make the corresponding atom, that is of Cl, to pull towards itself. So the pulling force towards the center of the point of the bond length is nothing but the restoring force, that is the force or the energy to pull the hydrogen atom towards itself or to its parental position by Cl atom is nothing but the restoring force. And also the restoring force will be equal to the distance of displacement. For example, if the hydrogen atom has moved 5 cm from its parental position, then the restoring force will also be 5 joules. And we see the derivation now. Now taking a simple case when diatomic molecule may be considered as a simple harmonic oscillator, that is oscillator in which the restoring force F is directly proportional to the displacement. So as I mentioned earlier, the restoring force will be proportional to or equal to the displacement in accordance with the Hooke's law, and thus we have F which is directly proportional to X here. F is the restoring force and X is the displacement. And we'll consider a constant, that is force constant. So applying the force constant, we'll get equation number 1, that is F is equal to K into X. And we'll write another equation for X, that is displacement. X is equal to nu minus nu E. Here R is the distance which the atoms have been stretched and RC is the equilibrium distance between the two atoms. The factor K is called as the force constant. So the constant which we are considering here is the force constant. So if x is equal to 1 centimeter, K is equal to minus F. Therefore, force constant may be defined as the restoring force per unit displacement of a harmonic oscillator. Here we can see what this force constant actually refers to. So the restoring force per unit displacement. For example, if the atom has moved 5 centimeter and if we have to, the energy required by a force to pull back to its original position A. So the force which is required to pull back the atom by 1 centimeter, 1 unit is nothing but 1 centimeter here. So force constant is nothing but the restoring force per unit displacement of a harmonic oscillator. So to pull back the atom by 1 centimeter is the force which we need, and it is defined as a force constant. And it is found to be related to the equilibrium vibrational frequency omega oscillation. And according to this equation, omega oscillation is equal to 1 by 2 pi into square root of K by mu, which is equation number 2. And we know already mu is the reduced mass. Or this equation can also be written in another form, that is omega dash oscillation is equal to 1 by 2 pi C into square root of K by mu. And to calculate the value of K, that is force constant, equation 2 can be written as K is equal to 4 pi square omega square oscillation mu, or else we know that mu is a reduced mass which is expressed in terms of m1 m2 whole divided by m1 plus m2, and where m1 and m2 are the masses of the oscillating atoms respectively. And thus, by knowing the vibrational frequency omega oscillation of a mass of an atom of a diatomic molecule, the force constant K can be calculated. And we should also make a note that omega oscillation is expressed in terms of per second. If omega oscillation is in centimeter inverse, then multiplying the above equation by C square, that is, we get the final equation K is equal to 4 pi square C square omega square oscillation into m1 m2 by m1 plus m2. So this is the equation which we use to calculate the force constant when we have a diatomic molecule or also even polyatomic molecules. But this is especially used to calculate the force constant of diatomic molecule. Thank you for watching. If you have liked this video, kindly like and subscribe to the Luminous Science. See you all in my next video with problems related to molecular and vibrational spectroscopy.